All right, so now we're getting into chapter 10 here regarding gas laws. All right, so regarding chapter 10, the very first thing that you need to know regarding properties of gases, so there's a total of 4. The first one is that gases gases can expand and compress. So they are compressible and expandable. And because of this, gases have variable shape and volume. So they have variable shape and volume. The third property is that gases mix uniformly. All right, so those are the 4 properties of gases. Gases are compressible, they are expandable, they have variable shape and volume, and they mix uniformly. And the sixth concept here, you should know what gas pressure here is, its definition, the different units of pressure, and also how to convert between pressure units. So by definition, gas pressure is the result of constantly moving gas molecules striking the walls of their container. So in physics, again, pressure is force per unit area. It's the force applied divided by area. And so gas molecules are traveling, they're moving around constantly, striking the walls of the container. So they have a force and then they strike a wall, the wall of container, and in a, with a specific area, right, a spot. And so pressure is dependent upon the force applied, and also the area of in which the force was applied. Okay, so that's the definition of gas pressure. Another type of pressure is atmospheric pressure, and this is essentially pressure that we are experiencing in the environment. It's the result of the air molecules in our environment. Another thing that you should be aware of is the definition of standard temperature and pressure. This is STP. The standard temperature is 0 degrees Celsius or 273.15 kelvins. And the standard pressure is 1 atmosphere or 760 millimeter mercury. And here are the units of gas pressure. So there's atmosphere, inches mercury, centimeters mercury, millimeters mercury, torr, psi or pounds per square inch, and kilopascal. And kilopascal is the official SI unit of pressure. So let's take a look at a few examples of converting between units of pressure. So the example here we have 12,300 kilopascals, and we want to convert this to pounds per square inch. So let's take a look. All right, so in this table right here, it tells you the equivalence of the different units of pressure. So we are converting kilopascal into pounds per square inch, PSI. So this is the equivalence. 14.7 psi is equivalent to 101 kilopascals. So what we can do here is we can multiply this given value by the equivalence, right? So we're going to put kilopascal here at the bottom, kPa, and then psi, the unit that we want, up top. Okay, and the equivalence is 101 kilopascal equals 14.7 psi. All right, so you can see how the units cancel out here. kPa and kPa will cancel, and then all you have to do is plug this into the calculator. 14.7 times 12,300 divided by 107. So we get 1690 psi. All right, and we can do the same thing here for 940 torr. So we're going to multiply this by the equivalence factor between torr and psi. So again, we have psi up top, and then the unit torr at the bottom, and 760 torr, according to the table, equals 14.7 psi. All right, so torr will cancel out, and we're left with the unit that we want. So 14.7 times 940 divided by 760, and we get roughly 18 psi. And the last one here is 39.8 inches of mercury converted to psi. So again, psi up top, inches of mercury at the bottom, and the equivalence is 14 psi, 14.7 psi equals 29.9 inches of mercury. All right, so inches of mercury will cancel, leaving us with the unit that we want up top, which is psi. So 39.8 times 14.7 divided by 29.9, and we get 19.6 psi. All right, that's how you convert between units of pressure. The other concept that we talked about in chapter 10 is the different variables that affect gas pressure. So there are a total of 3 different variables that we covered. And the first one is, so I'm just gonna write all 3 of them here. We have 3 variables. It's N, T, and V. Okay, so we have N, which is the number of molecules or number of moles. Number of moles or number of molecules. Okay, T is for temperature. And V is for volume. All right, so these are the 3 variables that affect gas pressure. So if you're thinking about gas pressure in terms of frequency of collision, then how do you think the frequency of collision will be affected by these 3 variables? So if you are just thinking about, let's say, the number of moles or number of molecules, and keeping the 2 variables constant, they're not changing, then increasing the number of molecules would result in the increase in gas pressure, because now you have a bunch of molecules in a container, let's say a small container, and increasing the number of molecules would increase the rate of collision or the frequency of collision inside that container. And so increase N results in increase in pressure. If you were to decrease the number of molecules, you would also decrease pressure. Okay. Temperature is the same way, right? If you're keeping the number of molecules and volume constant, if they're not changing, and the only thing that you're changing is the temperature, that would also increase the rate of collision, the frequency of collision inside the container, because you're giving these molecules more kinetic energy. And so they're going to be moving a lot faster, hitting the walls of the container, colliding with each other a lot more often compared to at a lower temperature. And so in that case, increasing T, the temperature, would also increase pressure. Okay, if you were to decrease temperature, then you would also decrease pressure. So as you can see in this relationship here, both N and T increases with pressure. They are directly related to pressure, both N and T. Volume, on the other hand, is the reverse, right? They're inversely proportional. If you were to increase volume and keeping N and T the same here, then volume would change, right? So let's say that we increase volume, that would decrease pressure. Again, the reason why is because you're keeping N and T constant in order to, so if you were to increase the volume, you're expanding the volume, the molecules inside the container will have more space to roam around, right? They have more space, and that would result in less collisions, right? It would take them longer to hit the walls of the container because they have to travel farther away, right? If you were to increase the volume or the size of the container. Same thing if you were to decrease volume. So if you were to decrease volume, now these molecules inside the container have shorter distance to travel. They'll hit the walls of the container right away at a smaller size. And so that would actually increase the rate of collision and therefore increase the pressure. So these are the variables that affect gas pressure. So we covered different gas laws in this chapter. There's Boyle's law, Charles's law, Gay-Lussac's law, Avogadro's law, and 3 or 4 others. So let's take a look at every single one of them. And again, this is related to pressure, number of moles, temperature, and volume. In terms of Boyle's law states that pressure and volume are inversely proportional. So they are inversely proportional. So if you increase volume, you would decrease pressure. If you were to decrease volume, you would increase pressure. Okay, and he proved this mathematically using his equation P1 times V1 equals P2 times V2. Okay, initial pressure times initial volume equals final pressure times final volume. So let's take a look at this one example here. it says a gas occupies 12.3 liters at a pressure of 40 millimeter mercury. What is the volume when the pressure is increased to 60 millimeter mercury? So the first thing you want to do here is to isolate the information that you need, right? We're going to extract the information that we need. So we have the initial volume of the gas, which is 12.3 liters. And then it tells us what the pressure is of this gas. That would be our P1, 40.0 millimeter mercury. Okay. And then it also tells us what the pressure that we're changing it to, right? So we're increasing the pressure to 60 millimeter mercury. So that's going to be our second pressure, our final pressure, P2. So the question here is, what would happen to the volume, right? What would be the volume if we were to increase the pressure from 40 to 60 millimeter mercury? So we're trying to calculate V2 here. What is the final volume? All right, so we're going to use this equation P1 V1 equals P2 V2 and solve for V2. Right, so V2, so all you have to do is isolate V2 by itself. So we're going to divide P2 on both sides. All right, so that's gets rid of P2 over here. So that basically cancels out, leaving us with what we're looking for, what we're trying to calculate, V2. So in that case, V2 equals P1 times V1 divided by P2. All right, now we can plug in the numbers. We have pressure 1, 40 millimeter mercury. And then we're going to multiply this by V1, which is 12.3 liters. And we're going to divide this by the second pressure, which is the final pressure, at 60.0 millimeter mercury. All right, so millimeter mercury would cancel, and we're left with volume in liters. All right, so plug this into the calculator, 40 times 12.3 divided by 60, and we get 8.2 liters. And if you want to follow the significant figures here, you would put another 0 here, 8.20 liters. All right, and the second gas law here is Charles's law. And Charles's law basically states that volume and temperature are directly related. So volume and temperature are directly related. So that means that if you were to increase the temperature and keeping the number of moles and pressure constant, then volume has to expand. Okay, so this is when N, the number of moles and the pressure are constant. Okay, and he proved this using his equation V1 over T1 equals V2 over T2. Okay, initial volume divided by initial temperature equals final volume divided by final temperature. And you want to make sure the temperature is in kelvins. Okay, you got to convert it in kelvins. So here's an example. We have 4.40 liters of a gas collected at 50 degrees Celsius. What would be its volume if you cooled it to 25 degrees Celsius? So again, we're going to extract out the information that we need. We have the initial volume, which is 4.40 liters. We also have the initial temperature, which is 50 degrees Celsius. And we're going to go ahead and convert this to kelvins by adding 273. So that would be 323 kelvins. And then we have the final temperature here, T2, which is 25 degrees Celsius. All right, so the question here is, what would be its volume? That would be the final volume. So looking at the equation here for Charles's law, we have to isolate V2, right? So how do we do that? How do we isolate V2 by itself? So we have V1 over T1 equals V2 over T2. So all you have to do is cross multiply. So we're going to move T2 up here, and then we're going to leave V2 on this side. So now we have V2 equals V1 times T2 divided by T1. All right, so that's the equation that we need. And all you have to do now is plug in the numbers. So we have V1, which is 4.40. And we're going to multiply this by T2, which is 298 kelvins. And then divide that by T1, which is 323 kelvins. All right, you can see that the kelvins will cancel out and we're left with the volume in liters. So 4.4 times 298 divided by 323 equals 4.06. So it would decrease to 4.06 liters. So if you were to decrease the temperature, volume would also decrease. Again, that's according to Charles's law. V and T are directly related if we were to keep the number of moles and pressure constant. Increasing temperature would decrease volume. Decreasing temperature would decrease volume, as you've seen here. So it decreased from 4.40 to 4.06. All right, and the third gas law here is the Gay-Lussac's law, which basically tells you the relationship between pressure and temperature. So Gay-Lussac's law states that pressure and temperature are directly related. And they are directly related when N and V, number of moles and volume, are held constant. They're not changing. All right, so if you were to increase temperature, you're also increasing pressure. If you were to decrease temperature, pressure would decrease. So here's an example. Well, the equation is P1 over T1 equals P2 over T2. Again, you want to make sure that temperature is in kelvins. All right, so here we have a constant volume of gas that has a pressure of 0.350 and a temperature of 50 degrees Celsius. What is the pressure when the temperature is doubled? Okay, so according to Gay-Lussac's law, if you were to increase temperature, you would also increase pressure. So you would expect pressure to increase here. And again, it says constant volume, so we don't have to worry about that. So we're going to extract out the information. We have pressure here, the initial pressure, which is 0.350 atmosphere. We also have temperature here. This is our initial temperature, 50 degrees Celsius. 50 degrees Celsius, 50.0. And the question is, what is the pressure when the temperature is doubled? So if the temperature was doubled, T2 would be 100 degrees Celsius because we're doubling it. So now I can convert them to kelvins by adding 273. So you're going to have to double it before you convert it to kelvins. So 50 plus 273 is 323 kelvins. 100 plus 273 is 373 kelvins. So the question now is, what would be the pressure, the final pressure, at 373 kelvins? All right, so again, this is our equation right here, and we're trying to determine what P2 is. And so we're going to move this T2 to the left-hand side of the equal sign, and we can do that by simply cross-multiplying. We're going to move T2 upstairs. All right, and that isolates P2 by itself. So P2 equals P1 times T2 divided by T1. All right, so all you have to do now is plug in the numbers. We have P1 here, 0.350 ATM, multiplied by T2, which is 373 kelvins. And we're going to divide that by T1, which is 323 kelvins. And you can see the kelvins would cancel out, leaving you with the unit of pressure, ATM. All right, so plug this into the calculator, 0.350 times 373 divided by 323, and we get 0.404. All right, so that would be the final pressure if we were to increase the temperature. So as you can see, according to Gay-Lussac's law, increasing the temperature would increase the pressure. By doubling temperature, we would increase the pressure as well. So it increased from 0.35 to 0.404. So we've seen Boyle's law, Charles's law, Gay-Lussac's law. The fourth gas law is Avogadro's law. So as you're familiar with Avogadro's number, and that's related to the number of moles. And so according to Avogadro, the number of moles and volume are directly related. So that means we're going to keep volume, I'm sorry, we're going to keep pressure and temperature constant. So the only thing that's changing here is number of moles and volume. So the equation is N1 over V1 equals N2 over V2, or V1 over N1 equals V2 over N2. It doesn't really matter. So that means that if you were to increase the number of moles, volume should expand. right? Or if you were decreasing the number of moles, volume would decrease. So let's take a look at this one example here. We have 5 liters of gas containing 0.965 moles of gas. If the amount of gas is increased to 1.80, what would be the new volume? Again, it says pressure and temperature are kept constant. So let's take a look. So we're going to extract out information. We have the volume of the gas. The initial volume was 5.00 liters. We know the initial number of moles, which is 0.965. And then we're increasing the number of moles, N2, to 1.80. So according to Avogadro's law, you would expect the volume to expand here. So that's our V2.
Professor, we can't see your writing.
Oh, thank you for that. All right, so here it is. All right, so again, these are the information that we need. Now we have to set up our equation. How do we determine V2? All right, so we're trying to isolate V2 by itself. So what you can do here is we can just take the reciprocal real quick. So we're gonna do V1 over N1 equals V2 over N2 because we want that V2 to be in the numerator. And then we're gonna move N2 to the left-hand side to isolate V2 by itself. So again, cross multiplication, and that isolates V2 by itself. So that would be V2 equals V1 times N2 divided by N1. All right, so we have isolated V2 by itself. All we have to do now is plug in the numbers.
Professor, I have a question.
Sure, go ahead.
So I'm just a bit confused. Earlier you wrote N1 over V1 equals N2 over V2,
Yeah,
and then switched the signs. Can you explain why you did that again?
over here. Like, why did I flip them?
Yes. Why'd you flip
Oh,
V?
it just makes the math a little bit easier to work. I mean, you can. So I just took the reciprocal here.
Okay.
Yeah, I mean, if you want to isolate V2 from this equation, I mean, they're the same thing. It's ratio and proportion,
Okay.
right?
Okay. I was just wondering.
Um, yeah, I mean, if you want to see it from this point of view, again, you want to cross multiply them, right? And this gives us N1 V2 equals N2 V1. And we want to isolate V2 by itself, so you can divide both sides by N1. And N1 cancels. And so what you get is the same thing by doing this method. So N2
Okay.
times V1 equals N1. Yeah.
Okay. Thank you.
All right, so now we're going to just plug in the numbers here. V1 initial volume is 5 liters. Multiply this the number by N2, which is 1.80. And then divide this whole thing by N1, which is 0.965. All right, so the moles would cancel out, and that leaves us with the unit in liters. And let's plug this into the calculator. We have 5 times 1.8 divided by 0.965, and we get 9.33 liters. So as you can see here, according to Avogadro, increasing the number of moles would result in the expansion of the gas. So you can see how the liters increase from 5 liters to 9.33. All right, another gas law that we talked about is the combined gas law. It combines the first three laws altogether. And so let's take a look. So combined gas law combines the first three laws. So we have Boyle's law, which was P1 V1 equals P2 V2. And then we're combining this with Charles's law and the Gay-Lussac law. So in the Charles's law, it's between volume and temperature. So V1 over T1 equals V2 over T2. And then the Gay-Lussac law is between pressure and temperature. P1 over T1 equals P2 over T2. So this is the combined gas law. So again, this combines the first three gas laws. All right, so that means, so we don't have the third variable here, which is the number of moles. So that means that N is constant. The number of moles isn't changing. So let's take a look at this one example here. We have 2 liters of a gas that's collected at 25 degrees Celsius and pressure of 745 millimeter mercury. What is the volume at standard temperature and pressure? All right, so let's extract out the information here. We have V1, initial volume of the gas, which is 2.00. We know the initial temperature, which we can go ahead and convert to kelvins, 25 degrees Celsius plus 273 equals 298. And then the pressure in millimeter mercury, which is 745. And it's asking what is the volume at standard temperature and pressure. So the standard temperature is 273 kelvins, 0 degrees Celsius. And the standard pressure is 1 atmosphere, and 1 atmosphere is equal to 760 millimeter mercury. So we got to make sure that the units match, right? So we were given 745 here, millimeter mercury. You can convert this to atmosphere or convert atmosphere to millimeter mercury. It doesn't really matter. Now it's asking what is the volume? What is the final volume? V2. All right, so we can use this equation here, the combined gas law, and isolate V2 by itself. So I'm just going to copy and paste this real quick. So here's our equation. And we're going to isolate V2 by itself. We're trying to solve for V2. So we have to move T2 to the left-hand side and the P2. So we can cross multiply. So T2 would go upstairs, P2 would go downstairs. All right, and V2 now is by itself. So V2 equals P1 times V1 times T2 divided by P2 times T1. So that's P1 times V1 times T2 divided by T1 times P2. All right, all you have to do now is plug in the numbers. Initial pressure is 745 millimeter mercury. Multiply this by V1, which is 2 liters. Multiply by temperature T2, which is 273 kelvins. divide this whole thing by T1, which is 298, times P2, which is 760. All right, so you can see millimeter mercury would cancel with this one down here. Kelvins would cancel, and you're left with liters, the volume. All right, plug this into the calculator. 745 times 2 times 273 divided by 298 times 760. And we get 1.80 liters. All right, so there's a slight decrease in volume if we were to decrease the temperature and increase the pressure. So that's what we did here. We decreased the temperature from 298 to 273, but increased the pressure from 745 to 760. So we'll talk about two more gas laws here, and then we'll take a break and then come back and cover the rest, which is chapters 12 and 13. And those are short chapters. All right, so second to the last gas law that we covered in chapter 10 was the ideal gas law. And the ideal gas law basically combines three gas laws. One is Boyle's law, the other one is Charles's law, and then the third one is Avogadro's law. Okay, so combining all three would give us PV equals nRT, the ideal gas law. So that's P times V equals nRT. And R here is a constant. It's the ideal gas constant. It has the same value every single time. It's 0.08206 liters atmosphere per mole Kelvin. So that means that if you're using this equation, you want to make sure that for volume you have liters, for pressure you have atmosphere, for number of moles that would be moles, and temperature has to be in kelvins. All right, so let's look at this one example here. A sample of gas at 25 degrees Celsius has a volume of 11 liters and exerts a pressure of 660 millimeter mercury. How many moles of gas are in the sample? So again, first things first, extract the information. So we have temperature, which is 25 degrees Celsius. And we can go ahead and convert this to 270 to kelvins by adding 273, and we get 298 kelvins. We have volume, which is 11 liters. And we have pressure. As you can see, pressure here is not in atmosphere. And so we're going to have to convert this. Okay, so we have pressure in millimeters mercury. We got to convert this to atmosphere. How do we do that? We multiply this by the equivalence factor. So it's, again, the unit that we want is atmosphere. So we want to put that up top. 1 atmosphere is equivalent to 760 millimeter mercury. So you're essentially just dividing 660 by 760. So you can see millimeter mercury canceling out. Plug this into the calculator, 660 divided by 760, and we get 0.868. And we're trying to find N. One other piece of information we want here is R, which is 0.08206. And what is N? All right, so here's the ideal gas law equation. And what we're trying to do is solve for N. We're going to isolate N by itself. So we can divide both sides by RT. RT would cancel on this side. So now we've isolated N by itself. So, excuse me. So N equals P times V divided by RT. All right, let's plug in the numbers. We have pressure, which is 0.868. Multiplied by volume, which is 11 liters. And then divide this by R times T. So our R is 0.08206 times T, temperature 298. All right, you can see how the units cancel out. We have atmosphere here and here. Liters cancel out. Kelvins cancel out. And what's left is the number of moles. All right, plug this into the calculator. 0.868 times 11 divided by 0.08206 and 298. So we get 0.390 mole. All right, and then the last gas law here can be tricky. This one is called Dalton's law of partial pressures. So here's Dalton's law of partial pressures. And there's several equations that you can come up with for Dalton's law. So let's take a look. So the easiest one, well, first let's explain what Dalton's law of partial pressure is. So if you have a mixture of gases in a container, let's say air, you have air in a container, and air contains carbon dioxide, nitrogen gas, oxygen, and some other gases in trace amounts. How would you calculate the partial pressure, the pressure of each of the gases in that whole container? So that's what Dalton's law is. It takes into account the individual pressures of each of the gases in a given container. So you can calculate the total pressure in a container containing different gases by simply adding the different pressures, right? So P total would be pressure of one gas plus the pressure of the second gas plus pressure of the third gas, and so on and so forth, however many different gases you have. Okay, so again, if you have a container here and you have oxygen gas, fluorine gas, nitrogen gas, and let's say uh, helium. Okay, you can calculate the total pressure by simply adding them all up. The pressure of the oxygen gas plus the pressure of the nitrogen gas plus P helium plus pressure of fluorine gas, F2. Okay, so it's as simple as that. You're just adding them all up. Another equation that's just as equally important here is um, this law of partial pressures combined with the ideal gas law. Okay, so the ideal gas law is PV equals nRT. So let's say that these gases are all in the same container, right? And so we can use this ideal gas law to calculate the total pressure as long as we know the number of moles of each of these gases inside the container. Because the volume and the temperature will be the same for every single one of the gases because they're in the same container, so they share the same volume and share the same temperature. So in that case, we can use this equation to determine the total pressure. So in that case, P total times volume equals the total number of moles of the gases in the container times RT. So in this case, for the P total, we can rewrite this equation right here. This is Dalton's law equation. So P total, in terms of this example shown here, would be equal to, well, let's see. So the pressure of oxygen gas times volume equals the number of moles of oxygen gas times RT. Okay, using the ideal gas law. We can do the same thing for the other gases like fluorine gas. Number of moles of the fluorine gas times RT. Pressure of helium times the volume is equivalent to the number of moles of helium times RT. We're just separating them into individual pressures. And then the last one is pressure of nitrogen gas times V equals number of moles of the nitrogen gas times RT. Okay, now in these equations here, we can isolate PO2, PF2, pressure of helium, and pressure of nitrogen gas. And then we can add them all up and we can get PO2, the total pressure. So let's isolate these individual gases. So PO2, pressure of the oxygen gas, is equivalent to the number of moles of oxygen gas times RT divided by V. Okay, same thing over here. Pressure of fluorine gas equals the number of moles of fluorine gas times RT divided by V. For helium it would be the number of moles of helium times RT divided by V. And the last one here, pressure of nitrogen gas equals number of moles of nitrogen gas times RT divided by V. So now we can substitute these equations right here into the Dalton's law equation for P total. Right, so P total then equals the number of moles of the oxygen gas because that's PO2 right here, plus the number of moles of nitrogen gas times RT divided by V, plus number of moles of helium let me create some space here. The last one here is plus number of moles of fluorine gas times RT divided by V. All right, and we can even simplify this further, this equation here, by factoring out RT over V, right? Because that's the, they have the same RT divided by V here. So we can factor it out of the equation, RT over V. And all you got to do now is add NO2, the number of moles basically. So that's number of moles of O2 plus number of moles of N2 plus number of moles of helium plus the number of moles of fluorine gas. So that's basically it. And this right here is your N total, right? Total number of moles. Total number of moles. All right, so let's take a look at an example on the next slide here. So here's an example. We have a mixture of hydrogen gas, ammonia, carbon dioxide, and nitrogen gas. Okay, we have 2 moles, 3 moles, 4 moles, and so on. And the total pressure of this mixture is 800 torr. What is the partial pressure of each gas in torr? All right, so this one is probably going to be a little bit more challenging, but this is the equation that we need right here. This is the equation that we're going to need. Okay, so we need to calculate the total pressure. And so all we have to do is add up the number of moles of the gases, right? Except we have different gases here actually. So we have hydrogen gas, ammonia, so I'm gonna have to change these. So what do we have here? We have hydrogen gas, we have ammonia NH3, we have carbon dioxide, and nitrogen gas. All right, so this is our N total. What is our total number of moles? So we're going to add up 2 plus 3 plus 4 plus 5. All right, so what do we have here? 5 plus 4 is 9, plus 5, 14. So we have 14 moles of gases. We know what R is. 0.08206 liters atmosphere divided by mole K. We also know what the temperature is. Actually, we don't. Okay. So we know the total pressure. All right, so we don't know volume and temperature here, but that's okay. We can calculate this because we know the total number of moles. So we can set up our equation here, P total, which we know, equals N total times RT over V. So what we can do here is solve for this right here temporarily. I mean, there's probably more than one way to do this. We can calculate what RT divided by V is even. We can calculate what this is, RT divided by V. So how do we do that? Well, all you have to do is divide the total pressure by the total number of moles. Okay, so RT over V equals P total divided by N total. Okay, let's do that first. So we have the total pressure here is 800 torr. I'm gonna have to create some space here. All right, so we have 800 torr here, but we have to convert this to atmosphere by dividing it by 760. So 1 atmosphere equals 760 torr. All right, so 800 times 1 divided by 760, and we get 1.05. All right, so now we're going to plug this number into this equation right here so we can solve what RT over V is. So that's 1 atmosphere, 1.05, divided by the total, which is 14 moles. and we get 0.075. We can round this to 0.0752. So this is our RT over V, right? So this is ATM per moles. All right. So again, this is our RT over V. So now we can solve for the partial pressures, because that's what we're trying to find here, the partial pressures. So the partial pressure of the, let's say, hydrogen gas is equal to the number of moles of hydrogen gas times RT over V. We know what RT over V is. We calculated that. It's right here. So all you have to do is multiply the number of moles of H2, which is 2 moles, times RT over V, which is 0.0752 ATM per moles. All right, so moles would cancel out. So 2 times 0.0752 equals 0.1504. And I know this is in ATM, so if you want to convert this to torr, multiply by 760. So that would be 114, roughly 114. All right, we can do the same thing for the other gases here. What do we have? We have moles, pressure of NH3, pressure of carbon dioxide, and the pressure of nitrogen gas. So nitrogen NH3 is 3 moles multiplied by RT over V, which is 0.0752. Number of moles of carbon dioxide is 4 moles. Number of nitrogen gas is 5 moles. All right, so we have moles canceling out. This one is 0.2256. This one is 0.3008. And the last one is 0.376. All right, and we can convert these to torr. This one is roughly 286. This one is 229. And the last one is 171. All right, so when you add up all these together, these numbers here, it should add up to 800 torr. So 114, 114 plus 171 plus 229 plus 286, and we get 800 torr. So that checks out because it says the total pressure is 800. All right, so I know it's 10:40. I guess we can take a 10-minute break and then we'll come back for the rest. And it shouldn't take more than 20 minutes for the rest. All right, so let's come back at 10:50.